All right, so today we're going to be talking about the conservation of energy. Again, we're going to be using our mind map notes for this quick little video on the conservation of energy. I think the mind map notes are especially important when we get into this unit on energy because we can really see the connection between some of these terms that we are going over. So our objective today is to be able to describe the law of conservation of energy and apply its principles to solve for the different types of energy. Your essential question, which you all should try to answer in about a 1 to 2 sentence summary, is how does the law of conservation of energy affect the energy of an object? So got kind of weird mind map notes written out for you all. So I'm going to actually start again from the bottom. So last time we talked about different types of energy here, right? We know that we've got chemical energy, nuclear energy, electromagnetic energy, electrical, thermal, and then the big one that we talked about was mechanical energy. Now, mechanical energy, remember, we have two different types of mechanical energy. We have kinetic energy and we have potential energy. Kinetic energy is our energy due to motion. So any object in motion is going to have a certain amount of kinetic energy. Potential energy, on the other hand, is energy due to position. So I kind of want you to think a little bit more deeply about what these terms really mean, right? Kinetic, the object has to be in motion to have kinetic energy, right? So we have to have a moving object in order to have kinetic energy. And that is because it is calculated using velocity. So if an object isn't moving, it doesn't have a velocity, and therefore it does not have kinetic energy. Same with potential energy. I want you to think about potential energy as, it's almost like it's pent up, right? So it's not moving, but it's anticipating moving. That's what I want you to think about when we talk about potential energy. So it's really due to position, right? If an object is at rest on a table right here, it's not moving, but we know that if we were to swipe this table out from under the object, that object would automatically fall down to the ground, right? So, and that would be transformed into kinetic energy. So we know that right now at rest, it has potential energy. But as soon as we swipe that table away from the object's energy is actually going to become kinetic because we know that object's going to fall and hit the ground. So this potential energy is I want you to think about it as kind of it's pent up energy. It's just waiting for something to happen to it. That's the energy that we're talking about when we think of an object's potential energy. So I kind of like to draw these little starburst symbols around an object with potential energy, indicating that it's not moving, but it's just got a lot of energy pent up and it's ready to move. It's ready to turn into kinetic energy. All right. So a couple equations to keep in mind as we are going through the lecture today. Remember that we do have our kinetic energy equation, which is Ke equals 1/2 mv squared. We also have our potential energy equation, which we will go through an example on how to calculate today. And the third equation I want to draw your attention to is our mechanical energy equation. So this is actually a new equation. We didn't go over this in the last video. But mechanical energy, given that there are two types of mechanical energy that we are learning, kinetic and potential. The mechanical energy I want you to think about as the total energy. So mechanical, and I'm still in highlighter mode. Mechanical energy is our total energy that we might have in a certain situation. So the total energy is going to be our two types of mechanical energy added together. And you'll start to see that play out in just a moment. Now I talked a little bit about in this potential energy example about how this object's energy could change to become kinetic energy. And that is possible through the law of conservation of energy here. So the law of conservation of energy, I'm going to highlight it here. States that energy can neither be created nor destroyed. It can only be transferred in a system. So another key thing to remember is that the total energy, the mechanical energy, will not change. So this allows us to have this equation here. And this allows us to have this equation here. Mechanical energy is equal to the kinetic energy plus the potential energy of an object in a system. So if we remind ourselves what a system is, right? It's an enclosed scenario, basically. So when an object is in a system, we're just talking about that one scenario. So in this upcoming example, we're talking about a baseball being thrown across the baseball field. That is a single system. So we are only concerned about this particular scenario. So a system is kind of like the scenario that we are working with in our physics word problems. So in a system, in a particular scenario, or in any physics word problem you might encounter in this class, energy cannot be created or destroyed. So if you're solving a physics word problem, you're never going to get more energy. The object is never going to gain more energy in that particular scenario. And it's never going to lose energy in that particular scenario. It is only going to be transferred between types of energy. So for example, you might have an object that starts off moving. So it's really only got kinetic energy because that's our energy due to motion. And then maybe it stops moving. That energy of the object is not lost. It has simply been transferred between, and I cannot spell today. That energy of the object is not lost. It has simply only been transferred from two different types of energy. I'm going to write E for energy transferred. And it could be transferred back as well, right? It could start off not moving, and then it starts moving, and that potential energy becomes kinetic energy. So let's go through an example of this. And I'm going to take my mouse, zoom it in a little bit. All right, so here's a particular example. A baseball is thrown across the field. If its mass is 1 kilogram and it reaches a maximum height of 5 meters, calculate its kinetic and potential at each point in its projectile motion. So the points that I'm referring to are these little blue highlighted dots. So I'm going to label them 1, 2, and 3. Now remember, when we talk about projectile motion, right, the object is moving here and it is moving here. But if it's a true projectile, it loses its motion when it peaks at the top of this curve here, right? It's kind of like your famous cartoon, right? Your character is blasted off. I don't know if y'all watch Tom and Jerry, but I feel like this happened a lot in Tom and Jerry. All right, so you have your cartoon character. He's blasted off in a rocket, in a jetpack or something, and all of a sudden his jetpack runs out of speed. And then you start to see him slow as he gets up to the top of his motion. Then he stops moving and he's like, oh crap, I'm going to start falling now. And then he falls to the ground. If you don't really understand that reference, I encourage you all to watch more cartoons. They actually have great drawn out visualizations of projectile motion. But anyway, so point I'm getting across is that it is moving at point 1, it is stopped at point 2, and it is moving again at point 3. With that in mind, that allows us to identify the main types of energy at these 3 points. So at point 1, if it is moving, we know that this is, I want you to picture point 1 directly after that ball is released from the baseball player's hand. So right as that ball is released, that baseball has kinetic energy. It is moving. It is being tossed in a certain direction. Then it reaches its overall peak of its arced motion, and it is no longer moving in the upward direction. So we're going to call this potential energy, right? The only place it can go from here is in the downward direction. So we know that this potential energy that it has at the peak of its motion is now going to transform back into kinetic energy. So we've got our 3 different points. We've also identified the primary type of energy at each point. So now we can actually go through and start piecing these pieces of the puzzle together. So I am going to go ahead and let's see what we have written out. We've already got our picture. We're doing our 4 steps to solving a physics word problem. I'm going to do step number 2 over here because we're actually going to end up with a couple different step 3s when we get to that in just a moment. So step 2, let's just go ahead and draw out what we know and what we don't know from the problem itself. So we know, according to the problem, and again, when you are figuring out what you know and what you don't know, I encourage you all to just look for the numbers in the problems. That's going to be your best indicator of what you know and what you don't know. So we know that the object has a mass. I'm going to highlight that. It has a mass of 1 kilogram. So I'm going to write M equals 1 kilogram. All right. We also know that it reaches a maximum height of 5 meters. So I can change this. Change colors. So I know that it reaches a height of 5 meters. I can go ahead and write that in here as well. All right. Another value we also always know, and since we're dealing with projectile motion, it is going to become important, is little g. That's our acceleration due to gravity, is going to be 9.8 meters per second squared. All right. And normally, again, acceleration is in the negative direction. So I normally would put that little negative sign there, but I'm going to just leave it out. And that is because since energy, we are eventually going to solve for energy, and I will write that here in just a moment. We know that energy is a scalar, so scalars don't care about direction. That negative sign is to indicate the downward direction of the acceleration due to gravity, but since energy is a scalar, it doesn't care about that downward direction, so we're just going to leave that as it is. So we know we are solving for a certain type of energy. We don't know what the object's kinetic and potential energy are at any point in its motion so far. So now we need to move on to step number 3. So we're going to figure out what energy makes the most sense to solve for first, given what we know from the problem. Now, if we go back down and look at some of our equations, we have our kinetic energy equation, which is 1/2 mass times velocity squared. And we have our potential energy equation, which is mass times the acceleration due to gravity times the height of the object. Now, given what we have written out here, we have a mass, we have a height, and we have gravity. The problem did not give us a velocity. So take a moment, think about what energy you might solve for first. Hopefully you came up with, all right, if we're not given a velocity, we cannot solve for these kinetic energies yet. I'll highlight those so it make it a little more obvious. So remember, kinetic energy is the main form of energy at both points 1 and 3 in the baseball's motion. We cannot solve for them yet because we are not given a velocity. You do need velocity to solve for kinetic energy. What we can solve for right now is potential energy. We are given the object's mass and its height. So I'm just going to go ahead and solve for position 2 first. So I'm going to write at position 2, which is mostly potential energy. We're going to solve for that one first. All right, so we know our potential energy equation is mgh. So now I can go ahead and start plugging things in where they belong and move on to step number 4. I'm going to leave potential energy here as is because we're still solving for that. I can plug in, I'm going to plug in my number for mass here, which I know from over here is 1 kilogram. Multiply that by 9.8, which is our acceleration due to gravity, and that is also equal to g. And then I'm going to also multiply that by the object's height, which we know from the problem at this point is 5 meters. Now, once I multiply all of those together, I get my potential energy at position 2. Which is going to be 49 joules. So we know at position 2 in the baseball's motion, that potential energy is equal to, I'm going to write that right here. That potential energy is equal to 49 joules. Put that in a box. All right. So we've solved for position 2. Now we got to go figure out what the kinetic energy is at position 1 and position 3. Now, I still don't have a velocity, so it's going to be very difficult for me to attempt to solve for kinetic energy when I don't have that object's velocity to plug into our kinetic energy equation. However, we did learn another equation. We know that the total energy is going to be equal to the sum of the kinetic energy and potential energy of the object across its motion. So like I said, this whole motion here across this, I'll get my highlighter out, this whole motion of the baseball is going to have a single number for the mechanical energy or the total energy. And we also know at position 2, there is no kinetic energy. That object has stopped moving at position 2. So if there's only potential energy and no kinetic energy at position 2, we can say our mechanical energy at position 2 is going to be equal to our potential energy plus our kinetic energy. And our mechanical energy for the entire path of motion is equal to our potential energy, which we already solved for, is 49 joules, plus our kinetic energy, which we know that doesn't exist at position 2, is 0. So our mechanical energy across this entire arc of the baseball's motion is going to be equal to 49 joules. With that in mind, we know that energy can be transferred. At positions 1 and 3, according to the chart, there is kinetic energy, but no potential energy. So if there's only kinetic energy, and we already know our mechanical energy, or there's only kinetic energy, right? If we plug this back into our equation here, we know our mechanical energy is 49 joules. And we know that 49 is going to be equal to our kinetic plus our potential energy at these 2 points. So our potential energy is 0 at both point 1 and at point 3. That gives us a kinetic energy of 49 joules. So at both points 1 and 3, that kinetic energy is 49 joules. There is no potential energy. So to sum up what is going on here, I'm going to make that a little more clear so that y'all can see that as a 4, not a 9. To sum up what's going on here, this object, this baseball, when it was thrown, started off with a kinetic energy of 49 joules. That it was also its total energy. It did not have any potential energy at position 1 in this motion. Then, as it traveled up the motion across the baseball field, it reached position 2. When it reached position 2, it stopped moving. Therefore, it lost all of its kinetic energy. That kinetic energy became potential energy. So the 49 joules of kinetic energy from position 1 to position 2 transferred to become potential energy. Notice those numbers are the same, 49, 49. The total amount of energy for the entire system is 49 joules. It just changes what type of energy it is. It changes from kinetic to potential. Once it reaches its total potential energy, it starts moving again. It drops back down. It continues moving across the baseball field in downward motion to the point right before it strikes the ground. It only has kinetic energy again. It does not have any more potential energy. So that potential energy that was at the top of its arch motion all of a sudden became kinetic energy again. So it switched from kinetic energy to potential energy back to kinetic energy. The total energy of the system did not change. And that is because of the law of conservation of energy. Total energy will not change. Energy is only going to be transferred between types. It can only be transferred from kinetic to potential and back to kinetic. All right, so I know that was kind of a difficult topic, and it's very abstract sometimes when we talk about the law of conservation of energy. So hopefully that explanation helped, but please make sure you're taking time to reread your notes, reflect on some things you learned from the video, and writing that 1 to 2 sentence summary. And please don't hesitate to come ask me any questions if you have them. I look forward to discussing this topic more with you all in class.